take.
Really nice take, dude.
All right, we got the 2200 grit sandpaper out. Kaz is in the building. 2, 3. That's it.
Hey guys, how's it going? Welcome to tutorial 5. Today we're going to be going over some simple examples that involve recursion, which is something you guys have seen in your last assignment and in this assignment. So there's three main topics we're going to go over, and we're going to cover how to code each one of these, and then at the end there's going to be time for any questions you guys might have. So this first one is pretty simple. It involves binomial expansion, which is something that you guys might have heard of. If you look over here, we basically have what a binomial expansion would lead to. And what we're trying to do with this problem that we're going to code up is given an exponent for some term like a plus b raised to that exponent, we want to find out what the coefficients would be if that term were to be expanded out completely. And of course, those coefficients correspond exactly to the terms on Pascal's triangle for that given exponent. So what we're going to be doing is we're going to take in an input, which is the exponent, and our output is going to be a list that contains the coefficients. So for example, if our n, which is our input, was 3, we would output a list 1, 3, 3, 1. And pretty naturally, there's a really good recursive process that we can use to obtain the results we need. So let's go over that. We can create a new cell here. And all right, let's go for it. So we'll take in our n as input. And for any recursive function that you make, I'm sure you guys know you don't want to go forever. So you need a base case that's going to terminate. So our base case here is going to be 0. We're going to basically assume that all of our input is going to be greater than or equal to 0. So if n is equal to 0, which is going to be our base case, we're going to return the appropriate answer, which is just a list containing 1, which if you reference the Pascal's triangle, all it is just the number 1, right? So that's a coefficient right there. And else, right, if n is not equal to 0, then we can actually derive the middle parts of the coefficients from the previous binomial expansion. So what I mean by that is, for example, let's take exponent 2. You have the coefficients 1, 2, 1. You can actually derive 1, 2, 1 from the one above it, 1, 1, simply by going okay, well, you can clearly see that the leftmost and the rightmost coefficients are always 1. And the middle coefficients, the one in between the left and rightmost coefficients, are basically the sum of these two coefficients. So 1, and then the sum of 1 plus 1 is 2, and then the rightmost 1. And then if we tried to go coefficient 3, we have once again the 1, and then you do 1 plus 2 right here, which is 3. You go 2 plus 1, which is 3, and then you slap on another 1 at the end. And that's basically the whole format. So we can write this recursively, and our recursion is always going to trail back all the way back to our base case, which is going to give us 1, and we can build any other binomial term expanded from that base case. So we can write that. Like I said, you're going to need your previous you say that there are zeros beside the first and last ones, and the whole thing follows that rule. True? Yeah, no, that's a valid point, Jared. We're going to keep coding this for all values other than n equals 0. You're going to need the previous binomial expansion term always, so we could instantly call that right now and just store it. You can say prev equals binomial expansion n minus 1. And now you want to create our output, which is what we're going to return. Our output, we can start it off with the first element of, okay, well, first off, the output's going to be a list, but we can actually start it off with the first element of the previous one, which is basically always going to be 1. So we could just say prev 0. Now, instead of doing these 2 lines, we can actually just initialize output as a list containing prev 0. We can save a line here. So what we can do is something like this. And now this line is no longer required. And now that we have our first term of the output done, we need to fill in the middle. And we fill in the middle, like I explained earlier, using the sums of the previous ones. So we can make a loop because we're going to have to iterate over the coefficients of the previous binomial term. And we can basically say for I in range n minus 1. And I'll show you why it's n minus 1. Because what we're going to do is we're going to append on the sum of I and I plus 1. So we want prev at I plus prev at I plus 1. And that's why it's n minus 1, because if we're accessing I plus 1, then when this will go to n minus 1, and we want to have minus 1 plus 1. And so this will basically be, we'll have n here, right? Which, if we were to go any further, you'd get out of bounds of your list. So they balance out, which is good. And that's all you need to do in your loop. And so that will basically fill in all of your middle terms. And now all you have to do is add on your last term, which is the same thing as your first term, which is just prev at 0. And once we're done that, we can return our output. And hopefully that makes some sense. We can run this and it compiles fine. And let's do some test cases. So we can say binomial, let's print the result of binomial expansion at 0, for example, is a good start. And obviously this just hits our base case and returns instantly. So we get that result. We can try 1. And you see it matches the Pascal's triangle because all we're doing is just, we're never even running through this for loop because n minus 1 would be for I in range 0. And so this never runs. And then we just sandwich on prev at 0, which is the 1 again. And I'm sure you can guess, as you keep going, the same recursive process continues, 2, 3, and you can even do 4. And they all match Pascal's triangle, which are the coefficients for a binomial expansion. So this is a really cool and natural application of recursion to find these coefficients. Does anyone have any questions about any of the code in this block? If not, then we can move on to the next problem. How would you do this in Haskell? That's a good question. You might want to email Pasara because I'm not too sure myself, but he could help you out. All right, if there are no more questions, we can go on to the next problem, which is, as you can see here, a simple recursive sort. And so what we're going to do here is we're going to use recursion again to implement a very simple sorting algorithm, which is in place. It updates the list that you're trying to sort. So since it's simple, we can call this simp sort. And this takes in a list, so we can say L. And the cool thing is we're going to have the same recursion. So you're going to have a base case. So if the length of that list is equal to 1, well, then the list is already sorted. You can just return L, right? Because that's your list, right? Your sorted list is your original list. And if the length is not 1, which means it's greater, then the way we're going to use recursion to sort this list is by actually removing the minimum and putting the minimum of that list at the beginning of the list, right? So we can store that. We can say let m equal the minimum of the list. All right, this is very easy Python to find the minimum. And then we can actually remove from the list that minimum. So now the minimum's gone. And now all we have to do is put it back into the list at the beginning. So we can return m as a list, which is the minimum, plus recursively sorting the list, right? And the reason this works is because we've removed the minimum here, right? So this recursive call is going to use this algorithm to sort the list with m gone. And once this returns, this recursive call will return the list sorted without that m. So then this return statement will sandwich whatever the result is. It'll just use list arithmetic here, right? And it will basically join these two lists. If you guys don't know, you can actually use arithmetic operators with lists. So this will return a list, and if you put square brackets around this value, it treats it as a list, and then a list plus a list is a list. And this would just put this before this in the elements. So we can do some more test cases here. We can say sample list. Let's do like just some random numbers. We can have repeating numbers, as you can see, because min will handle that gracefully. Python's min function will just take one of the minimums. It doesn't really matter which one. Cool, we have a list. And we can say sim sort, and we can pass in our sample list. And as you can see here beautifully, our list is sorted. And this was done by updating our list in place. So our list was literally changed one element at a time using the recursion and put back together so that our final result is sorted. This is a pretty simple algorithm, made really simple using recursion. But if anyone has any questions regarding anything done here, feel free to ask. We're actually going pretty fast. Considering we only have 3 things to do today, we're already done 2 of them. We're going really, really fast. Where would this be useful? Sorting is very useful in a lot of cases. There's going to be many cases when you're doing something in programming, because for this application, sort just seems better. Oh, okay. In that regard, okay. I thought you were asking why sorting itself was useful. So, yeah. The idea of this course is to teach you how to do certain things. And the one downfall with Python is that for a lot of these fundamental programming concepts that you have to do, like Python usually has a built-in function that does it with just that one function call, right? So yeah, you could always just use sort, which is Python's built-in sorting function, but knowing how to sort something yourself, or knowing how to find the minimum or maximum or sum or average, right, of any given input yourself is really important, because in the future, if you keep going with programming, you're not going to be doing everything in Python. And one of the reasons is because all these built-in functions that Python have, they're all really slow. And so you pay a big price in efficiency for convenience and simplicity, right? So that's probably the main reason. In this exact case, recursion is pretty slow, but it's still good to understand how you could sort something using recursion, right? There are many other sorting algorithms that have much higher efficiency and much better performance, right? But as a result, they're more complicated, which is a pretty great segue because no, I think you need to use SimSort for your life. But I was gonna say this segues pretty well into our next problem, which is merge sort, because merge sort is a substantially more complicated sorting algorithm, but we reap the rewards by having a much better runtime. And that's really good because as your sample size grows to very, very large numbers, the difference between a solution that runs in something like n squared versus some solution that runs in log n is massive, right? We can start coding up. So I'm assuming there's no questions for binomial expansion or SimSort. Jared, I wasn't actually using merge sort as an example. I was just saying something that runs in n squared versus something that runs in log n is a huge difference. But yes, merge sort, the efficiency is actually n log n, and we're going to cover why it's n log n in this tutorial. You guys are going to learn a lot more about merge sort and sorting algorithms in future lectures with Professor Moore, but this is a pretty good introduction, and it will really kind of serve as a good introduction as to the idea behind merge sort and how you would implement it. But I'm sure Professor Moore will go a lot further into the details. So let's get started. All right. Well, let's call this array. This function is again recursive. Merge sort is recursive. The idea behind merge sort is that you kind of split your list into two halves, and then you sort both of those two halves, and then once they're sorted, you can merge those two sorted halves into one list, right? And the idea is that all those recursive calls go deeper, go deeper, go deeper until they can't go any deeper, and you get a sorted list, and then the recursion pops back up one at a time, boop, 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 and they all get merged as they go up the recursive stack, right? I'm actually going to try and pull up quick picture that might help with merge sort a little bit. Show the merge sort simulation. That's maybe a good idea. Since we're running pretty well for time, that might actually be a pretty good thing to look at. Jeffrey Wang, is this a stable in-place algorithm? Good question, Jeffrey. You're displaying some pretty strong knowledge for a CompSci 1MD3 student, but if I remember correctly, merge sort is stable, and I don't think it sorts in place. Actually, I know it definitely doesn't sort in place. But thanks for the question. Okay, so let's find that video. I think that's going to be good. Okay, I don't know how good this video is going to be, but we're going to find out. Oh no. Wow, this is going fast. Okay. Alright, I think we should slow some of this down, maybe. Let's just watch it once. You guys don't need to read the text right now. Just try and look at the actual pictures, see what's going on. And that's our sorted list. Cool. All right, so let's go back and look at it one step at a time. Okay. So they asked some questions here. We have a left index and a right index, where we basically are using these indices to keep track of where we are in the list. And these indices move. So we start left all the way here, we start right all the way here. We ask ourselves, is the left index less than the right index? And since the answer is yes, right, we set a variable m equal to L plus R minus 1 over 2. So that would be basically in the middle, right? Which is why it's called M. We're trying to find where the middle is, because we're going to use that middle to split the array into two, all right? So M ends up being right here, right? So we split the array into these two parts. You end up getting this subarray and this subarray, right? All we did is just split them. And we asked the same question. Is L less than R? Yes. We're doing this for both subarrays. This is kind of the idea behind the recursion. And so we keep splitting. We keep splitting. We keep splitting. That's why it's recursive. Until we basically end up with individual elements, right? This is if you keep going down until the very end of the recursion. You'll end up with 38, 27, 43, 3, 9, 82, and 10. These are all individual. Now we can start putting the pieces back together by merging them. And this is what's happening at the smallest level all the way back up to the highest level of the recursion. If we skip past, what ends up here is that when we merge them in sorted order. So we want to put this list back together, and we're going to pick the smallest element first. So we want to put 38 and 27 back together, but we pick the smallest one first. Smallest one is 27, so we put that into our list. The next one, obviously, is the only one left, so it's 38. We do the same thing for all of these sublists, right? So 43 and 3 become 3 and 43. 9 and 82 stay as they are because they're already in sorted order. And 10 is in sorted order on its own because it's a subarray of length 1, right? So by definition, something that's size 1 is sorted. And now, as we go up the recursion, we're trying to put these two subarrays together, right? So initially, with 38 and 27, these were two subarrays. We put them together in sorted order. We did the same thing with this subarray. Now we're trying to put these two subarrays, both of length 2 each, back together. So we do the same thing, right? 3, we take a look at every step of the way. We look at both sorted arrays, and we pick the smallest one. So the front of this array is 3, and the front of this array is 27. Which one is smaller? 3. So we take 3. Now the front of this array is 43, and the front of this array is still 27. Which one is smaller? 27. Now the front is 38 here and 43 here, and we take the smaller again, which is 38, and the last one obviously is the one remaining, which is 43. And we do the same thing on this subarray. The subarray got sorted. We want to merge it here, so we pick 9 because this is the front of this array, which is the smallest one, and then 10 because 10 is smaller than 82, and then we get 82, right? And now our job is to merge these two subarrays, right? That's the whole idea behind the recursion of it, is that we sink all the way down to the deepest recursive level, we sort and we merge as we come back up the recursion, right? Which results in, as we go back up the recursion, our lists get sorted. We're doing the same thing here. We go 3, because here we were comparing 3 and 9, right? We're always comparing the front of either of these two arrays because the front is always going to be the smallest one because those subarrays are sorted, right? They were sorted earlier on in the recursion. So 3 versus 9, we pick 3. 9 versus 27, we pick 9. 10 versus 27, we pick 10. 82 versus 27, we pick 27. 82 versus 38, we pick 38. 82 versus 43, we pick 43. And then the last one remains is 82. Does anyone have any questions about the logic behind this merge sort? The recursive part might not make too much sense right now. And the hope is that hopefully after we code it up and demonstrate it, it'll make a lot more sense. And keep in mind, you guys haven't actually learned about sorting or merge sort yet in lecture. And that's going to happen in a very detailed manner in your lectures very soon. Yeah, so the idea for this one, and by default, whenever you hear someone say sort, the assumption is that it's low to high. If the objective is to sort something from high to low, then there will usually be distinction made to indicate that you're actually sorting from high to low as opposed to low to high. All right, so looks like no one has any questions regarding the logic. Yeah, this was a really fast video, so it was very helpful to pause it and comment along the way. All right, let's go back to our merge sort and let's think about what we want to do first. So if the length of our array is greater than 1, then we can sort it. If it's not greater than 1, then we can't really sort it, and we can just return whatever we have freely. So we can just cover right now the case for if the length of the array is greater than 1. We want to find the midpoint of the array, right? We don't really need to define indices for the left and right now because we kind of already know where they are, but we will soon. Here, once we know that our length of array is greater than 1, we want to find the middle. So we can set mid to, really it's going to be the length of your array divided by 2, but we're going to integer divide because obviously if it's an odd number, we don't want to have a decimal. We want this to act as an index, right? And for it to be an index, it has to be obviously a whole number. So this is just going to round down. It's going to take our length and divide by 2. And now is the part where we're going to split our array into 2 halves, right? So that we can sort it recursively. So we can make up a half called left. And we can use Python slicing to do this very easily. Just like that, right? I'm sure you guys remember that the second argument for a slice is always exclusive, just like for range functions. And we can do the same thing with the right and go from mid to the end. And right, you might think, oh, there's an overlap, right? You're counting the middle element twice. But no, because this is exclusive and this is inclusive. So we don't actually count mid when we do it as the second argument of a slice. So the right array is the one that actually includes the middle element. All right, and here's the cool part. For now, it might not make much sense, but we can actually call merge sort on both of those halves, because that will take it down the recursion. And based on what we do next, if any of these recursive calls end up having an input argument that has a length that is not greater than 1, then nothing's going to happen, because this is all in the if block for if the length of the array is greater than 1. UV, time complexity is n log n for all cases. That was actually explained earlier, so maybe you just joined. But glad to see you around. All right, here's what we're going to do. We're going to set up these loops using while loops. I think while loops are pretty appropriate for these kinds of problems because it really helps illustrate what's happening with the indices. I think Professor Moore actually mentioned this in a lecture, but someone asked in chat why he used while loops so often instead of for loops. And he gave an answer, which was a very good answer, and it was about the fact that while loops are more explicit in what's actually going on with the indices instead of something being implicit and kind of under the covers, which can happen a bit with for loops. And it's also because Professor Moore came from a much more OG programming background, and he coded in Visual Basic, or Basic, sorry, and he had a lot of like he had to keep track of all of his indices himself. So when you carry that experience over, it makes a lot more sense to use while loops because you're so used to keeping track of indices yourself. Cool. So this is what we're going to do. We're going to copy over our data from those arrays to our actual array. So I'll try and code this up a bit, and if it doesn't make too much sense right now, it will after we're done. And I can go back and revisit any confusion points, right? But what we're basically going to do, first we should initialize our variables. We're going to say I, j, k, 0, 0, 0. We're basically initializing 3 variables to 0, and they're going to be our counters, right? And we're going to iterate over the left and the right, and we're going to ask ourselves, is L at I less than R at j? And if it is, then the array at k is our third counter here. It's our third looping variable. We're going to assign that to L at I, right? Because if L at I is less than R at j, then we want to pick that one to put in the array. And if that happens, then we want to increment I because now we want to update the front of the left array. If you remember from this video, whenever we picked something, we move the front index, right, the pointer that points to the front, over by 1, and that's very similar to what we're going to be doing here. So we want to do I plus equals 1, and if L at I was not less than R at j, which means that either they're equal or R at j is less than L at I, then we're going to do the opposite, right? We're just going to add, we're going to assign the array at k to R at j. And we're also going to increment the pointer for that variable as well. Here's the thing, right? Regardless of whether L at I is less than R at j or the other way around, right? We want to increment k because every time we assign something to array at k, whether it's from L at I or R at j, we want to move it so that we don't assign a new value to the same index at k. So down here, we can say k plus equals 1. Cool. And that covers it for the copying of the data. Here's the thing, right? With our while loop here, we're only doing this loop as long as both of these conditions are true, right? We're only looping if I is less than length of L and j is less than length of R. And there's one issue with that, and that's the reason why we're not done right here, is that consider the fact where obviously one subarray is longer than the other, well, this loop, like you're going to iterate over this whole loop. Let's say length is smaller than L is smaller than R. L is smaller than R. Sorry. You're going to finish iterating over this whole loop, and there's still going to be a value in R. Which this is fine to do, but all it means is that we have to add over a check where we fill in any elements that might have been left over, right? So we can do that simply by just continuing with our while loop, but we just do another while loop. And this will take care of if there's an element left in L that we need to add to the array. We can just do array at k equals L at I. Oops, that's not right. And obviously increments I and k in this case, because we know that we're never going to have to get anything from R in this case because R is done. We've completely iterated through R, and all is left is L. So we can increment I, which is our pointer for L, and k, which is our pointer for the array that we're adding to. And we can basically copy this code over because we're going to do the same thing for the other subarray. But we're just going to, oops, change it to R and change it to J. And that's pretty much the whole program, unless I missed something. But it's a very intuitive program. I think splitting up into parts like these that have logical purposes is really helpful for understanding what's going on. And hopefully these indices, these looping variables, these counter variables, pointer variables, whatever you want to call them, make a bit more sense now. They were what we were using to keep track of our array and our left subarray and our right subarray. So let's make a quick function that, let's make a quick function that actually prints our array in a neat way. We can say for I in range of the length of that array, we'll print array at I, and a space after it, let's say. And we can just print an empty line here, which is like this is just like printing nothing. It's gonna print a new line. It's equivalent. So let's try this out. We have our two functions defined. Our merge sort is right here. Our print array is right here. And let's see if it works. How about we use the same sample list as we used earlier? We can define our sample list right there. We can print, we can say original array. How do you want to do this? I guess we could just say print array. Or actually, maybe we should add a new line here. For anyone who doesn't know, \n is the way to type new line characters. Alternatively, we could just add another print statement here, right? It does the same thing. So we can print our sample list. And this is going to print our original list, right? Now we can actually merge it. And since this merges in place, right? Or it merges without returning a new list that's separate from the original. It actually updates the list. We can just call merge sort on the array. And then we can do the same thing. We can basically copy this over, and we can say sorted array is equal to this. So let's give this a run and see what happens. We get a type error. All right, good thing it's just our print, at least yet. Oops, I should have cast that to a string because this is a number and we're trying to concatenate it to a string here, which is a big no-no. So let's just do that. Or you know what we could do? Instead of doing that, we just do that. Oh, that's horrible. Why is it doing that? Original array. This is just a, why is it doing one line each? Oh, of course, because I'm printing them individual times. So by default, the end of a print statement is a new line. So you can actually change that yourself by doing end equals. And this is actually going to change the new line, like the ending character of a print statement from the default new line to a space here because we specified it to be a space. So hopefully that works. It does work. And bonus, our array sorting algorithm, merge sort, works perfectly fine too. Here's our original array as shown, and we have our sorted array. So yes, this array sorting algorithm was significantly more complicated than SimpSort, but is it more efficient? Yes, quite a bit. Are there big differences in the efficiency of different sorting algorithms? Yes, there are. And there are prices you pay, but benefits that you reap for each one respectively. So knowing about the different sorting algorithms and their different properties is very helpful, and it's something that you're definitely going to learn a lot more about in lecture. I'm going to save this, and I'll upload this Jupyter Notebook to the Avenue page under the tutorial content page. So in that folder, you'll find tutorial5.ipynb, which is this file. Does anybody have any questions about merge sort right now? Whether it's about the logic or the code that we just implemented? If we have time, can we time them actually? Oh, 2 questions, they both want to see the time differences. Sure. Yeah, let's do that. I actually don't really know how to time stuff. I believe it's like time.time in the time module. So we'll try that out and we'll see what happens. Let's try. We can do start time equals time.time. We'll run our merge sort here. Let's make some space. And then we'll say print time elapsed. And then we'll say time.time minus start. Make the sample input a random list of like 10,000 elements so the difference is noticeable. Nice. Let's actually do that. Yeah. You definitely wouldn't notice the difference with a sample input of something so small. So let's go over here and we'll say big input equals a list. And we'll say for I in range 10,000. Big input dot append. We also need random. We'll say random dot randint. Say 110. I think they're both inclusive. For randint is kind of a weird Python function, but I'm pretty sure actually both arguments in randint are inclusive. So this will go 1 to 10. So we should have, hopefully, Let's try it out. We should have a very, very big. Okay, there we go. That's our input. That's a lot. So let's open this back up. We have 10,000 elements here that are all between 1 and 10. And so now we can run, hopefully, this time thing. Start is not defined. I thought oh, oops, start time. I'm not a bucket. I'm sorry. Yeah, that was my bad. But yeah, guys, so it actually takes no time, which is pretty incredible because that seems to break some laws of physics for sure. It's doing sample list. Wow, that's true. That's true. All right, maybe I am a bucket. Let's try again. Cool. So this is measured in seconds, I'm pretty sure. So we're taking 0.07. So roughly 70 milliseconds, I'm pretty sure, 77 milliseconds. Let's try bumping it up by a factor of 100. Let's do actually 1,000 and seeing how that works. Okay, so you notice that our code is still running, and increasing inputs by a factor of 1,000 when you're dealing with an efficiency of n log n is actually a huge, huge increase in size. So let's actually interrupt our kernel. We'll restart it. We'll save again. Let's not make it that big. Let's do 100,000. It's taking time. Okay, and there we go. We even got an error. That's how bad it was. But our time was 1.12 seconds. So let's bring our simp sort back into play and see how long that takes. All right, and we're going to do the same thing. We're going to copy this over. And we're going to simp sort our same big input. And let's actually bring this down. Let's bring it back to, let's actually do 1,000 first, just in case. I don't really know how simp sort's going to do. All right, am I forgetting anything, or is this good? I think this should work fine. Simp sort's not defined. Let's bring simp sort. I really thought, let's try again. Okay. All right, there we go. Wow, Asing, you did the math. That's cool. 210 seconds. It's like 3.5 minutes. It's a bit too much right now. But there you go. So for this one, for this input size, do you need to reset the big input? Jared, when we rerun the cell, like every time I rerun the cell, big input is recreated and repopulated. So that happens automatically here. So those are the differences in seconds between merge sort and simp sort. Let's try bumping up the sample size. Oh, in between the calls. Oh, shoot, true. So yeah, okay, yeah, let's do that, let's do that. So this is pretty messy code, and we definitely could be putting some of this code in functions and do function calls instead, because you have a lot of repeated code. But we're just trying stuff out, so we're not really going to do that right now. Let's actually keep it at 1,000 and see how it does. Okay. So merge sort, a lot faster, almost 10 times faster here. 4 milliseconds versus like 30. And if we bump up the size to like 10,000, So merge sort is already done in 90 milliseconds, and simp sort is still chugging along. Oh, and we passed Python's recursion depth. So it looks like simp sort toppled over real quick. Yeah, and that shows you kind of not only the time that recursive functions take when using when dealing with big inputs, but also the memory, right? Like they're very costly. So you pay quite a price for having clean, simple recursive functions, but doing things iteratively. Or okay, well actually, sorry, they're both recursive, but this is just a lot worse recursive. Oops. Yeah, n log n versus not n log n. Some sort was no match for chat sort. True, true. We'll bring that down back to 10 or just 1,000. I'll save this. Actually, I'll run it, and I'll save it again. For merge sort, it divides the length by 2, but can we make it divide by 3 and see how it goes? I think this is actually as far as I want to go with merge sort for this tutorial. You can divide by 3 and see how it goes, but yeah, I really want you guys to be able to hear the description of merge sort from Professor Moore first in the lectures and really cement it, and then we can revisit some concepts like varying some of the parameters in merge sort, and as well as visiting other sorting algorithms, which we definitely will do, I think. Can't you manually set the recursive depth? I don't think you, I don't know how to. Let me check. Oh, maybe you can. All right, guys. Let's give that a shot. So it looks like we can run this code. I think we need to import sys then. We're doing that. And manually set that. I don't know. Actually, let me check what it is by default. Or I guess I can print it. That's not good. Built-in function set recursion limit. Oh, it's set recursion limit. So let me try this. Are you serious? Oh. Oh, it's a function, so let me just call it, I think. Huh. Nothing. Should we print it? Usually there's output though. Guess there wasn't. It's 3,000. Okay, thank you, Jared. So let's go back to set recursion limit. And we'll set that to, wait, so did we just pass in a function? Can we say like 6,000? It's not like equals, right? It's definitely not equals. That's not right. Oh, now maybe it is equals. If it's a constant, then there shouldn't be time change. If they if they differ by a constant, like you won't really be able to notice a time difference. Like yeah, because it doesn't really scale with the input, right? So maybe it is equal to like, yeah, guys, this is all for fun, really. But hey guys, first, like, if anyone has any questions regarding the actual logic here with any of these functions, feel free to ask, because we're basically done tutorial content. Everything we're doing right now is just messing around with merge sort and simsort and seeing how they compare. So hopefully that works. So what did we try last time? We tried 10,000, I think. So we'll do 10,000 here and there. And once again, our merge sort finishes. Apparently you're supposed to write it like this, sys.setRecursionLimit. Oh, no. GG boys. Okay. Let's try again. Well, I tried that. I tried I tried sys.setRecursionLimit. And called it, but it said int is not callable. So simsort is not defined. Oh, I need to run simsort again now to define it. Yeah, see, oh no, it works. Oh, it works. Okay, that's super weird. Let's try. I don't know if changing it from 3,000 to 6,000 was enough. It clearly was not. We're gonna try one more time. We're gonna try one last time. I'm gonna go here, and we're gonna change this to like 60,000. That should really work. We might be sitting here for a while if it does work, because this could take forever. All right, I'm gonna stop trying, guys. Clearly, simsort is no match. It was beautiful, and it's still our creation, and we should still love it, but it doesn't really put up a good fight against merge sort, or most of the other popular sorting algorithms for that matter. So what I'll do is first I'll get rid of all this weird stuff that I added. Change this back to 10 or just 1,000. First run simsort. Cool. So this is what I'm going to upload to Avenue, because I feel like this is probably the best representation. And that's it, guys. Thank you very much. This is a really fun tutorial, actually. You guys will definitely go over this stuff in lecture, and it will probably be explained in theory a lot better than what I did here. But nevertheless, I hope you guys enjoyed it, and I'll see you next Monday. Take care, guys.